But basically, what I will present to you is that we propose a method to make the conical shells using the technique of the printing of composites. So I would like to acknowledge the contribution from my master's student, Mr. Mahmoud Fereidouni, and we are from the Concordia Center for Composite at the Concordia University in Montreal, Canada. So basically, what happened is that we take a look into the way how people, there are many applications where the conical shape is made. Suppose you have something like the nose cone of an airplane that is a conical shape. You can have something like the reduction area in the rockets. For this case here, you have something like a nose cone for a jet engine, or any kind of location where you have to reduce one kind of diameter to another diameter that you need to have a cone. So basically, there are many methods that people have used to make cone structures. Okay, so these methods consist of sheet wrapping, electroplating, filament winding, or hand layup. So the first two here, sheet wrapping or electroplating, can apply for metal or any kind of materials, but filament winding and hand layup mainly are for composite materials. So in terms of the, so this case, we talked about the sheet wrapping, in the sense that the way you do that is that you need to have a mantle, some kind of a mold. And the mold can be made out of wood or out of metal, and the mold need to have the conical shape. Then you take a sheet of that material, either plastic, paper, or whatever, and you wrap it around this kind of a mantle. And after that, then you just kind of join the seam together. But this kind of technique has some kind of issues in the sense that if you don't do a good job, you may have wrinkles, and you have the edge alignment, and you have to join the edge together. So that is one kind of technique that people have used in making the conical shape. Now, people in the NASA back in the 1960s, what happened is that they were trying to understand the behavior of the conical structure for space applications. And what they found that the previous method of kind of wrapping around like this give some kind of a result in the sense that they were doing some kind of buckling, the axial buckling load over the cone. And there was somebody that was also deriving an equation to predict the buckling load for the cone. And the experimental result is about 30% of the calculated result. So people thought that there was some kind of problem with the edge, and they were trying to make some other way, trying to really see whether you can make a more perfect kind of a cone structure so that you wait and the experimental load can agree with the calculated load. So the people in the NASA, what they did is that they were doing some method called electroplating, in the sense that they used also some kind of a mold, and then they put that inside an electrolytic chamber, and they were depositing, they plating copper on top of the mold. And from there, they obtain a conical shape that is very thin. But that way, they manage to get something that is that has no edge, and they manage to really do the experiment on the cone. And so this case here, they get the result, but still they did not agree with the calculated value. So the value they obtain is about 60%. The experimental value is about 60% of the theoretical value. But this case, this kind of a method has some kind of a, certainly has no edge, but it can only be used for metal only. And also for the case of electroplating, you can only manage to get very thin structure, something like a fraction of a millimeter. So the case of composite, people have also made composite cone. And one of the techniques that people use to make the composite cone is use filament winding. You can see you have, first you need to have a mantle, and then you are winding the kind of fibers on top of that. So this you can see that you have, this is the meridian. I mean, it depends on the angle that you want to wind. But what happened in the case of the method is that because of the fact that you have smaller diameter at one end and larger diameter at another end, so the case of filament winding, it ends up that you don't have the same angle. You don't have the same fiber angle. So the fiber angle is defined as the angle between the direction of the fiber and the meridian. So here, for example, you have θ1 at this location, and you have θ at another location. So the issue with this filament winding method is that you have the variation of fiber orientation along the length. And also, because of the fact like this, that you also have the variation in thickness. That means you don't have uniform thickness over the whole surface of the cone. And also the case of filament winding, it is difficult to place fibers along the 0 degree. Now the 0 degree, that means along the meridian, difficult to really get that kind of a placement of the fibers. So again, the people at NASA and the people working in the Ariane company, the space people, they really want to really see whether they can make something that has a good kind of performance. So people went to the extent of doing a hand layup, in the sense that you have a mantle, and you cut out strip of the fibers and you lay them on top of the surface of the mantle. So this case here, then you can really. So, I'm sorry. Okay. So this case here, then you're doing the hand layup. You got strips of the composite and you lay on top of the mantle. So this case you can do that at 0 degrees. For example, you can have strip of 0 degree, but you have the situation of the lap and gap. In the sense, you have some location where you cannot really cover the surface, and you have to cut some kind of partial kind of fiber to place over the surface. Or if you have something you want to make an angle of the fiber angle of 30 degrees, then again, you have to cut very kind of complicated shaped strips to be able to do that. So this kind of a technique certainly give you a good structure in the sense that you can control the fiber orientation. You may have uniform thickness, but it is very laborious, it is time consuming, and also it is error prone. So there was a publication in 2015 where they described this technique, but I could not find any kind of result in terms of the work that they can try to really obtain the axial buckling load. I could not see that. So basically the work had tried to develop some kind of technique to make by hand layup. So that means that in the case of the conventional method, the method that exists right now to make the shape of a cone, they have something in common. That means they always have a mold. You always need to have a mold to do that. And the case when you make a mold, I mean, it is costly, it is time consuming. And also in the case when you do something using carbon epoxy, then you need to cure it. That means you need to put that inside either an autoclave or in an oven to be able to heat up the resin to cure. But if you want to make a large structure, then there is a limitation in the size of the autoclave or the oven to be able to do that. So basically that is so-called the kind of state of the art, the way how people do to make the conical shape. So we talked about the 4D printing of composite. In the case here, the way we start working with the 4D printing of composite over the last few years. And we have made a few things. And basically, I think that I have probably presented this to some of the people here before, in the sense that the way that people manufacture composite material is that you use something we call a pre-preg. Now the pre-preg here, I mean, you have the carbon fiber embedded inside the epoxy resin. And you cut the pre-preg down into different sheets and you can lay them up into different orientation. Like this case, you have 0, 90, 45, and so on. Then after that, you put that inside an oven autoclave to cure and you get a piece. So basically that is the conventional way of doing composite manufacturing. And so this case here, the way that we use in terms of making the composite, we use an automatic fiber placement machine. Now, this machine can lay down the continuous fibers, carbon epoxy, along a certain orientation, and you can vary the orientation of the fiber to make the different kind of layup sequences. So the thing that the kind of main mechanism that we use in for the printing of composite is that we use unsymmetric laminate. Okay, usually most of the people do composite manufacturing, they use symmetric. Symmetric, that means that you have a layup sequence that is symmetric across the mid thickness of the laminate. For example, you have the layup sequence of 0, 90, 45, minus 45, and you put the S as symmetric. That means that the 4 layers below the midplane is exactly the same as the 4 layers above the midplane. And the reason why people want to use symmetric laminate is because they don't want to have the laminate to distort. You start with a flat layup, and at the end you obtain a flat laminate. But the case of 4D printing of composite is that we want the flat laminate to become a curve. So that's why we use unsymmetric. You use something like a 090 laminate configuration. So that way that you start with a flat stack of the pre-preg, and by the time you cure it, you cool it, you obtain a curved structure. So for example, here, that means the main kind of mechanism we use here is use a layup sequence to create the kind of a change of the shape from flat to curve. If you use something like a 90-0 layup sequence, then you end up with this kind of a downward bending structure. If you change the order of the layup sequence from 90-0 to 0-90, then you have a layup sequence, then you have the end up structure with the thing that is concave upward. And if you use something like 0-45, layup sequence, and in addition to the bending, you also have the twisting as well. So basically, that is the kind of idea behind the 4D printing of composite method. And also in this case, after you lay down the material, the stack of the material, you have to cure it. You have to heat it up to 177 degrees centigrade. You hold it for 3 hours, you cool it down. So this is basically a standard conventional way of making composite material. And also we use commercially available materials. So far, I think that over the last few years, we managed to make a few structures using this kind of technique. And what the structure we made is the word Concordia. Concordia, that means you're going to have the letter C-O-N-C-O-R-D-I-A. So each of the letters has some kind of curvature, but we only use a flat mold to make them. So in this case here, that means I showed you the configuration to make the letter A. For the letter A, this is the layup sequence. These are made mainly on the flat mold. And by the time you finish curing and cooling, it curves up to give you the shape of the letter A. So basically, that is the kind of the technique that we use. Another thing that we have done is the making of the leaf spring. So this case here, you can see the leaf spring. These have some kind of a certainly high stiffness and high strength. And in the sense that these springs are placed beneath an automobile, and it's used to support the weight of the car and also to control the vibration. So people have made composite leaf spring before, except that they have to use a mold. They use a curved mold. They lay the composite on top of the mold, and by the time you finish, you have the shape. But by using the technique of 4D printing of composite, we don't use a curved mold. We use only a flat mold. And we play again mainly with the layup sequence. So you can see here you have the layup sequence that we use here is 36 layers of 90 degrees and 24 layers of 0 degree. And in this case here, that means we obtain this kind of a structure. Again, I mentioned we only use a flat mold. By the time we finish curing and cooling, it gives you this shape. So this structure has an elastic constant of 486 Newton per centimeter. So that means if you apply the load here, then the ratio between the load and the deformation is 486 Newton per centimeter. And this number is comparable to the kind of spring that are used commercially available right now. And we also subject this kind of a leaf spring to fatigue loading. That means that we press it down to be flat, and we relax to be curved up and down through more than 1 million times, 1 million cycles, and there is no sign of degradation. So this case, it can show that it can really subject to fatigue load, and it has some kind of a practical stiffness value that can be used. So this case here, I mean that the thing that I want to mention is the layup sequence that we have is most important. And so going to the topic of making the conical composite shell. So we have to make the conical shell using the technique of the printing of composite. So this case, that means that we use the experience that we have done in the past. In the past, what we have done is that we lay down straight fibers, and the fibers are laid down in 0 and 93 degree orientation. And then if by the time you finish curing and cooling to room temperature, then you obtain this cylinder. So by using a straight fiber, you have a cylinder. Then in the case of if you want to make something like a cone, that we thought initially maybe what we do is that we just use the same kind of straight fibers, except we cut the edge. We have the edge here that has some kind of a shape of a trapezoid, and maybe that'll give you the shape of a cone by the time you cure and cool it. But in reality, we did not get that. Basically, what you get is only what we call a partial cylindrical shell. So this is not a cone in the sense that you have the curvature at the top and the curvature at the bottom are the same, except that at the bottom you have a bit less of the kind of a piece rather than the thing at the top. So this kind of a layup sequence does not give a cone, but it gives you only a partial cell. So how to get a cone? Basically, the way we do that is that we use a curvilinear fibers. In the sense that here we curve the fiber. We prefer to be along this kind of direction. And we also another kind of fiber along the radial direction. So this case here, that means you have the curvilinear fibers and radial fibers. And from this, if you do like that, then you obtain the shell structure. In the sense that you have the curvature at the top here is not the same as the curvature at the bottom. You have a bigger circle at the top and you have a smaller circle at the bottom. So basically that is the idea in terms of making the conical shells. So what happened is that if you do that by hand layup, you cannot make this kind of structure. So you have to use an automated fiber placement machine. it has the capacity to steer the fiber. So this case, you can steer the fiber along some kind of a curvilinear direction. And you can also make the fiber along the radial direction. So in terms of schematic, in terms of step-by-step procedure, the way how to do that is that at the beginning, you lay down the radial fiber. So this case here, you make the first strip of the fiber. Then you the next one, you make another strip. You have 2 strips, 3 strips, and then you continue doing this kind of situation until finally you have the whole surface of the trapezoid. And then after that, you lay down the other kind of direction of the fiber. You have the circumferential fiber, the first strip. You have the circumferential fiber, the second strip, third strip, and finally you have the total strip. So that means you have 2 layers, one along the radial direction, another one along the circumferential direction. So this one here shows you a photo of the kind of layup that was made. So in the sense that we have already made the radial fiber, and here we are now making the circumferential direction fiber. And so you start with a flat laminate, this kind of a curve, and then after you cure it and cool it, you obtain this cone shape. Okay, so basically that is the way how you can do that you don't need to have a mold. There is no mold in this case. So this case, then we can get the shape, but again, you wonder whether you can get some kind of a mechanical load, in terms of the axial compression. So this case here, then we join the seam together using some adhesive, and then we subject it to mechanical load. We put that inside the MTS machine, and you load it up. In this case, you can see that under this kind of loading, it shows you the buckling mode that you have. And in terms of the result here, we load it 2 times, and it buckle. When you unload it, it recover the shape again, and you do the load again. So here, this one here, you show you the first loading, and you hear this one show the second loading. So the load we obtain is about 16,500 Newton. And you wonder how much is that 16,500 Newton? You take a look into the weight of a car. The weight of a car is around 3,361 pounds, or 14,950 Newton. So basically, this kind of a cone with a mass of 44 grams and with a thickness of 0.4, less than 5 hair diameter, it can support more than the weight of a car. So that is the case. So that means that in conclusion, we can say that we demonstrate that the 4D printing of composite can be used to make composite cone without the use of complex mold. And these structures also have good mechanical properties suitable for practical applications. I thank you very much. I thank you the financial support from the Natural Sciences and Research Council of Canada. And I thank you for your attention.